Hello everyone, welcome to COMP382. In this video we are going to talk about regular expressions. Actually, regular expressions is going to be just another notation to specify a language. So I'm sure that you have heard about regular expressions and already have been actually using it. There are plenty of different applications. For example, in every Unix environment, regular expressions are used in the shell scripts. For example, in different command line like grep, sed, in many different actually editors like VI, in language in scripting languages like Perl script, or even actually in regular programming languages. In different programming languages, always there is a library for regular expressions that you can actually write it to do the pattern matching. Or for example, in lexical analyzers like lex and flex, which are used to write the compiler, the first phase of the compilers. So, what is the relationship between regular expressions and our discussion? The thing is, regular expression is in fact a notation to specify a regular language. So regular expressions, just like finite automata, which shows a language, they also they are equivalent. In fact, both regular expressions and finite automata, they are different representative of regular languages. Finite automata is more like a machine for us that you actually give it a string and it tells you yes or no, and in this way it represents the language. And regular expression is more like you just write a syntax that shows that okay, the language is going to show this set of strings, all the strings that can be matched to this regular expression. So as I said, regular expressions are going to be equivalent to finite state. What does this equivalency means? It means that if a language can be represented using a regular expression, you can write a finite automata for that, which means that its language is going to be a regular language, and vice versa. If you have a regular language, it means that you can write a regular expression for that. So I'm going to talk about this equivalency later. First, I need to define regular expressions formally for you. So before we go to the formal definition of regular expressions, because it depends on definition of some operators, I need to define three operators first, then I will give you the definition of regular expressions. The first operations that we have is union. The union of two languages, in fact, is going to be the union of the set, both sets of the languages. So each language is going to be a set of strings, right? So the union of two languages is going to be the union of those two sets. For example, if L1 is a set of these two strings and L2 is the set of these three strings, L1 union L2 is going to be all the strings which are either in L1 or L2. The other operator is going to be concatenation. So concatenation is concatenation of two languages, L1, L2. Let me actually show it to you in this way, that so the concatenation of L1 and L2 will be all the strings that can be created by concatenating one string from L1 to another string from L2. So the set of all those strings. So it's just like if for example, L1 has two members, two strings, and L2 has three. In total, you are going to have 6 different, not necessarily different, but 6 strings at the end that some of them might be actually similar. It just depends on what are L1 and L2. So the first string that can be generated is this string multiplied by, concatenated to this string, which resulted this one. Then this one concatenated to this one, which is resulted this one. The first one again concatenated this one, which is resulted this one, and the rest of them is going to be the concatenation of this one to all of these 3 strings here, which resulted these strings. So let me now formally define, write down the formal definition of these 2 operators. Assume that L1 and L2 are 2 languages over the same alphabet. So they are going to be some subsets of sigma star. Right, both of them are going to be a set of strings from sigma star. So we can define the union operator of these 2 strings, L1 and L2, to be all those strings which are either in L1 or L2. And this is the example that we saw. And the concatenation is that the concatenation of 2 languages is going to be the set of all those strings that those strings which is created from concatenating xy, where x comes from L1 and y comes from L2, which here is the example for that. Those are the 2 operator. This third one is killing closure, or we call it a star operator. Remember, we defined the sigma star and different powers of sigma. We can define different powers of any set of languages. The powers of any language. So the power 0 of any language, doesn't matter what is L, the power of the language L is going to, the power 0 of language L is going to be only epsilon. Okay, this is like a rule that it doesn't matter what is the language, the power 0 of that, this is going to be only epsilon, just like for the sigma. The power 1 of the language will be equal to the language, so all of the strings in the language. The power 2 of the language is just like you concatenate the language to itself once. Okay, so concatenation is kind of similar. Concatenation over the sets here for us is going to be similar to multiplication in numbers. You can just think about it in that way. So when you concatenate the language to itself once, so you concatenate them, so L concatenated L, this is going to create L power 2. So this is going to be the definition of this set of strings. So L power I is going to be the concatenation of L to itself I times. So this is going to be the set of all strings which is created from the concatenation of 6 different strings, not necessarily different, actually 6 strings, all of them coming from the same language L. Okay, so you can have duplications here. So for example, if 1 belongs to L, right? So the 1, 1, 1, 1, 1 is going to be a part of L power 6, right? And actually all other, for example, if 0 and 1 are a part of that, so 1, 0, 0, 0, 0, 0, this is going to be a part of L6. It's just, concatenating L 6 times. So here is actually just a recursive definition for L power I, just if you are interested in that. Always recursive definitions are useful because they will help us in the proofs. So based on that, here we can define the star operator. The star operator over L is going to be the set of all strings, coming from the union of all the different powers of L. So you can see that I here is just greater than or equal to 0, and it actually tells you that arbitrary number of concatenation. So I can go to infinity. Arbitrary number of concatenations. So for example, if L is just, for example, two strings L and double 0, L power 0, remember, this is the rule. L power 0, whatever is the language power 0 is going to be the epsilon. L power 1 is going to be equal to L, so this is going to be 1 and double 0. L power 2 is going to be the concatenation of L twice, so I mean probably, yeah, to itself. So 1 1 1 0 was 0 0 0 0 1 and this, so all of the concatenations, right? And so on. You can actually define the rest of them, and L star is going to be the union of all of these sets of strings that can be created. So a couple of special notes about clean closure. So if L is a set of strings that the size of it is greater than or equal to 1, it means that it has at least one member, and that member is not equal to epsilon. That's one member that you have is not equal to epsilon. So definitely L star is going to be infinite. The size of L star is infinite. So there are two cases that L star is going to be equal to only epsilon. Those two cases are going to be where L is just the epsilon, or L is empty. So L is empty, it means that it doesn't have any string. But still, L star is going to be equal to epsilon because L power 0 for all the languages is going to be the set of epsilon, only epsilon. Okay, so these are just listed those three operators that we defined: concatenation, union of two languages, clean closure over the languages, and you can also define positive closure, which this one is not a valid operator. The main three operators that we are going to use are going to be these three, but this one is more like a notation that positive actually closure, not clean closure, positive closure will exclude L power 0. So as I said, this operator is more like a definition. This is not the main operator that we are going to use. So here the question, one question for you. So if we are not including L power 0, does L plus positive closure going to contain epsilon or not? And the answer is that it depends on L. Because we actually include L itself in L plus, so in fact epsilon can be in the L plus if epsilon is a part of the language. So now I can define regular expressions formally. This definition is a recursive definition, in fact. So first of all, we have an alphabet, which is going to be, we call it sigma. Always, when we are talking about some strings, we need to define the alphabet, right? And the base of the definition. So we say that the base regular expression that we have are going to be the simplest form of regular expressions that we can have are going to be empty, which actually represent the nothing, no string in fact, epsilon, which represent the epsilon string, so epsilon is a valid regular expression, okay? And A, which is going to be all of the symbols of the alphabet, so all of single symbols of the alphabet are going to be, each one is going to be a valid regular expression. So now let's, the recursive part of the definition, assume that if R and S, both of them are two regular expressions, two shorter regular expressions, you can create larger or longer regular expressions by applying the operators over R and S. So this little r is going to be a regular expression, little s is going to be a regular expression. The thing is that little r is going to represent a set of strings. Let's just call that big R, and s is going to represent a set of strings. Let's call that big S. So the union of R and S, which we represented using plus in our notation, in different textbooks actually you might actually see different notations, but the definition of all of them are the same. They just, the symbol that we use might be different. So R